The time we took an image, we knew we were golden, that those stars had clearly moved.
The first order of business was to see how large the object is, to weigh it by measuring its gravity.
So we have the black hole here, and then the more massive it is, the more pull there is. The more pull there is, as it gets close to the black hole, the faster it goes. And we are measuring the speed of these stars. That's the key to getting the masses, measuring the speed of those stars.
Andrea's more advanced telescope made the difference. The object weighed in at a staggering 3 million times that of our Sun. But that didn't prove it's a black hole. It could still be a cluster of smaller objects. For the Germans, it was time to even the playing field. The VLT, Very Large Telescope, opened its doors on a mountain in Chile. Both the VLT and Keck were upgraded with revolutionary technology. For years, the teams relied on computers to pinpoint the location of stars through the turbulence of our atmosphere. Now, they could cancel it out with a new system known as adaptive optics. It uses a powerful laser beam to read the turbulence. Telescope operators can use those readings to sharpen the image of distant stars and galaxies.
So this little animation shows you the benefit of adaptive optics. So you see the stars without adaptive optics, you turn the adaptive optics on, and all of a sudden you see stars. And in particular, you see stars near the center of the galaxies. We track all of them, but these are the ones that are the key to the problem.
These new eyes were delivered just in time. With both teams watching, one of the stars made a dramatic hairpin turn around the center.
In 2002, it made a huge jump to over here. So it went whoop, all the way around.
The star was initially going very slowly and then moving around very quickly, and at that point coming very, very close to the central black hole.
And it's moving on order 10 million miles per hour, so it's just speeding away.
The star had come close enough for the teams to see that it had to be circling a single massive object.
All other physical explanations of what was at the very center were gone. The only thing left was a black hole.
To astronomers around the world, the evidence was impressive.
I have to say, when I first saw Andrea's video, I was stunned when I saw that star come out of the left side of the frame and go zipping around and go shooting off into the other end of the frame, and it moved around a point in space, and nothing was there.
That we could, with our instruments, together with our minds, effectively travel to the center of the galaxy, 26,000 light years away, and collect the evidence for such an incredible object was really an amazing achievement.
The European and American teams had confirmed that a black hole was there without actually seeing it. From our quiet corner at the far edge of our galaxy's spiral, it's hard to imagine the violence at its center. The closer you draw toward the center, the denser it gets. Our destination, the galaxy's central hub, brimming with stars, known simply as the bulge. Venture into the bulge and you enter a busy highway. It's jammed with star traffic speeding in every direction, and it's always rush hour.
There's a lot of gas. There's a lot of dust. This is absolutely the most crowded place in our galaxy.
There will be stars all around us, an incredible density of stars. I mean, we couldn't exist there. There's lots of ultraviolet radiation, X-rays are floating around, gas clouds bash into each other, a lot of activity. It's a very hostile environment, really.
The black hole is surrounded by a cloud of super hot gas that's falling in. The space around the black hole is so warped, it distorts the light that scatters across it. As bizarre as it seems, the gravity of a supermassive black hole is so spread out that you might fall in and survive for a moment.
During the final descent, you would then go into the event horizon, but you would actually not feel it because you are a small body compared to the large massive black hole.
Now, thanks to a computer simulation based on Einstein's own equations, we can visualize the scene. As you move toward the black hole's core, you hit an inner horizon, a logjam of trapped light and energy.
At a certain moment, as we hit the inner horizon, there's this infinitely bright, blinding flash of light. That's all the stuff that's been waiting there, trying to get out, is just held there at the inner horizon. It would vaporize you. Almost certainly, if you fell into a real black hole, you would simply, unfortunately, die.
But that's not the end of the journey. The computer storm can be turned off, and the strange predictions of Einstein's equations allowed to play out. A passageway opens up, a tunnel through space and time known as a wormhole. We now leave through a strange door known as a white hole. Here, the twisted logic of extreme gravity goes into reverse. Instead of being sucked in, you would be catapulted out to the far reaches of time and space. But to where? In science fiction, wormholes offer handy escape routes to other universes. In reality, the inside of a black hole is probably too chaotic and violent for a wormhole ever to form. The black hole at the center of the Milky Way is strange enough as it is. But is it the norm? Or is our galaxy a freak of nature? To find out, astronomers have mounted a major international project to search galaxies throughout the universe for evidence of supermassive black holes. From Apache Point in New Mexico, astronomers are probing big galaxies out to 1 billion light-years from Earth. They take a series of steel plates and drill holes to exactly match the location of galaxies in the night sky. Then they plug fiber optic sensors into those holes, and for the first time ever, they can use the plates to capture the light of hundreds of galaxies per night. The astronomers are looking for a distinctive light signature coming from a galaxy's core. It's a sign of hot gas swirling into a black hole. The goal of the project, called the Sloan Digital Sky Survey, is to map a quarter of the entire northern sky to find out what kind of galaxies make up our universe and how they are arranged. Of the 125 billion galaxies that make up the visible universe, more than 1 million have so far been analyzed. Nearly all the large ones, circled in red, bear the signature of a supermassive black hole.
The closer we look to the centers of galaxies, the more we find these black holes, and the inventory is rising high. So any idea for the formation of a galaxy will now have to include some explanation for how you get a black hole in its center.
But how did every big galaxy in the universe end up with a giant black hole in the middle? To understand, go back to the very beginning, the Big Bang. Matter and energy rush outward as the universe expands.
So you got the Big Bang handing you your birth ingredients, your hydrogen, your helium, your traces of some other elements. So it's kind of like this soup. You put it together and stir it.
It's gravity that stirs the soup. Over billions of years, it molds the universe into a spider's web of gas and galaxies. Within this web, gravity draws together wisps of hot, primordial gas. Over tens of millions of years, the clouds of hydrogen gas coalesce, growing more and more dense. sun grow hot enough to ignite. The first stars are born, giants, hundreds of times bigger than our sun. They burn out quickly and explode in the flash of a supernova. Billions of years later, an orbiting satellite called SWIFT is in position to capture that flash of light. SWIFT is the eyes of an international group of astronomers. Within 30 seconds of detecting a flash, it sends out an alert via mobile phones, pagers, and emails.
Adam, Mike Ford calling. We have a GRB detection. Please meet me at the observatory and call the GRB team.
The astronomers scramble to their telescopes. Speed is vital. They have to catch the light beam if they are to probe the dark secrets behind these distant disasters. First, they determine how far it has traveled, give it a name, and pinpoint its birth galaxy.
Then we're going to need to move the dome. Casey?
By analyzing the light, they have gleaned the distinctive signatures of black holes being born. The most distant are the earliest generation of primordial monsters.
We could be forming the seed of the supermassive black holes that we see in galaxies today very early on, when the very first objects form in the universe.
We can now, with our big telescopes, look back in time, and sure enough, what we find is that at the same time when the galaxies formed, also the black holes formed. It may very well be that they needed each other.
This computer simulation shows how our Milky Way galaxy was born. It grew over billions of years from a swarm of smaller galaxies smashing together, merging. In a cosmic dance of death, the infant galaxies swirl around and orbit one another, gravity pulling them closer.
If another galaxy comes too close, they will each feel each other's gravity. What started out as a stately ballet of stellar orbits moving around the center of their galaxy has now become this maelstrom. There's no other way to say it. Galactic cannibalism, that's what they're doing. They're dining on their neighbors, eating entire galaxies. Well, for every galaxy you eat, if that galaxy has a black hole in its center, it's going to eat the black hole. And the black hole will work its way down to the center of the large galaxy, making the center of the galaxy bigger as well as the galaxy itself.
As galaxies swallow each other, the black holes at their centers merge and grow.
And there was an epoch once, about 1, 2, 3 billion years after the Big Bang, when in fact galaxies were forming, or at least they were tremendously more active than now. And at the same time, black holes already existed, had formed, and were fed at tremendous rates, producing very powerful quasars.
Quasars are bright beacons of light at the centers of distant galaxies, where feeding black holes shine brighter than anything else in the universe. The Hubble Space Telescope peered into a dormant quasar in a nearby galaxy called M87. It found a tiny central region where gas is heated to tens of millions of degrees and whipped by gravity to millions of kilometers per hour.
What it became obvious was that there was a tremendous amount of mass in a very small volume. But that mass was very unlikely to be stars, like those stars that we see in our galaxy.
Astronomer Brian McNamara believes giant ravenous black holes can have a profound effect on the surrounding galaxy and beyond.
Can we get an offset?
180?
180, 180, same direction.
We are setting at 360, 360. Guider is locked up.
McNamara is studying a trail of devastation left in their wake.
Isn't that amazing? All of these other galaxies are gravitationally bound to